Hello again. Now we're looking at the two independent samples case. So here the idea is there is no natural pairing between the two samples. So when there is natural pairing, you'll be aware because it'll be fairly clear there's pairing there. Often, of course, here also the sample sizes are not the same, and that's another indication that these aren't paired. So as an example, I'm looking, for example, at the salaries between males and female executives. So here the independent, there's no pairing there at all. Population here, the first one has mean mu1 and variance sigma 1 squared, and the sample sizes will be n1 with sample mean x1 bar and variance s1 squared. The second population mean mu2 variance sigma 2 squared, and the sample size n2 sample mean x2 bar and s2 squared is the sample variance. So here the model is going to be, if I can write the model equation down here, it's yij is mu I plus eij. So here the I represents the population or the group number, and the j represents the observation number. So if you do more statistics at secondary or higher, you'll find these kinds of equations are very useful indeed. And of course, this is my random error terms. In other words, I'm saying the mean for y, the ith group is mu I. So the first group has mean mu1, the second group has mean mu2, and there's some random variation around it. So, excuse me. So the idea is I may have two different means. There's mu1 and there's mu2. And the observations here are just some random variations from the mean. So the observations here will be, the observation over there will be just this mean plus some random error. Another one here, this mean plus some random variation term. The same here, another observation here will be the mean here plus some random variation. So the observations from group 1 are this group 1 mean with some random variation. And the observations in mu2, the second group, are going to be mu2 plus some random variation. So that's what this means over here. So here the hypotheses of interest are going to be similar. Again, I'm going to say the mean difference is 0 versus 1 over either not 0 or 1 is bigger than the other. Essentially, mu1 take mu2 is bigger, which means mu1 is bigger than mu2, or mu1 take mu2 is less than 0, which means mu1 is less than mu2. So this depends on the question of interest. And again, the order of subtraction is important because how I subtract these things will depend on, will also just dictate how I subtract my actual sample means. Now, usually the standard deviations are unknown and have to be estimated. Now, the sample means may be different, as we saw earlier. I'm going to assume the variances are the same. Now, you'll find packages do this test without this assumption, but I'll always assume here that the variances are equal. There's lots of ideas and criticism on this. Many people say that if the variances aren't the same, you shouldn't compare the means of populations. And I won't go into the argument there, but we're going to assume that the variances are equal. If that's the case, how do I estimate the variance? Well, again, if I draw the picture we had earlier, I've got some mean over here and some mean over here. This is my x1 bar, sample mean, and my x2 bar here. So what I'm going to do is, I'm going to find the sum of squares over here first. And that's this much here. N1 take 1 S1 squared. That's the sum of squares for this data. And the sum of squares for this data is N2 take 1 times S2 squared. So if you remember the variance formula we had earlier for a single sample, S squared was 1 over N minus 1. Sum of the xi minus x bar squared. So this is my first sample, that's n minus n1 minus 1. And so what I'm going to do is, if I take this across to the other side, I'm going to get the sum of x1, xi minus x1 bar squared is just n1 minus 1 times s1 squared. And then I do the same to the other side. So this gives me the two variances over here. So I've got two sums of squares here. What I'll divide by here is going to be n1 plus n2 minus 2. So essentially, I'm weighting this variance by the number of observations, and then weighting this variance by the number of observations minus 1. I'm dividing then by the weights, the sum of the weights. So if you notice one thing here, the one I'm subtracting here in this case is because actually I have estimated one parameter from the data, which is x1 bar. In this case, to work out s squared p, the pooled variance, there are two means I've estimated from the data, that one and that one. So I subtract 2 off. So essentially my degrees of freedom here decreased by 2. In this case, the decrease was by 1 because I had one mean estimated, or one parameter estimated from data. I've got two things, x1 bar and x2 bar, estimated here. So I subtract 2 here. So my degrees of freedom reduces by 2. We'll find this as consistent in the work we'll do. The number of parameters we estimate in order to estimate your variance will be the amount by which the denominator will decrease here. So this is the sum of the sample sizes minus 2 here for 2 means. So that's my pooled variance. Then my test statistic, we know that if I use my results from my earlier work, or earlier work with sampling, is if I look at just assuming everything is normal, then x1 bar minus x2 bar, x1 is normal, x2 bar is normal, both of these are normal, so the difference is also normal. Their means are simply mu1 minus mu2, and their variance essentially for x1 bar minus x2 bar is sigma 1 squared over n1 plus sigma 2 squared upon n2. So I'm dividing by the square root of that, that's the standard deviation. That is going to be normal, not 1. And this is exact if populations are normal, and only approximate if populations are not normal. But then I'll have to have that each sample size is at least 30. Now, because I've assumed equal variances, I can replace the sigma 1 squared and sigma 2 squared by sigma squared. If I do that, the sigma squared can come outside this square root, and that becomes sigma, and I get this next line here. So the top's the same, but the sigma has come outside now, and I've got 1 over n1 plus 1 over n2 square root of. And this is again normal, not 1, because all I've done is standardize, taken the sigma out there. Now, if I replace the sigma by s, my sample variance, sigma squared by s squared, we know this becomes t. And again, this is exact if I start with normal populations, otherwise it's approximate. And if I have small sample sizes, I need to assume that populations are normal. Again, the order I subtract in here, you see the order I'm subtracting here will determine what my hypothesis as well. Example here, I've got 12 men with high blood pressure were given calcium supplements, that's meant to reduce blood pressure, and 16 men with high blood pressure were given a placebo. So we want to see here if calcium leads to a reduction in blood pressure. So here the two groups, sample size n1 is 12, the mean was 4.1, this is the decrease, and the deviation is 6.42. For the second group, 16 men, the decrease there was 0.03, and the standard deviation is 5.25. So the question here is, the reduction in blood pressure greater for group who received calcium supplements? So I model that as putting my mu1 and mu2 as the decrease in blood pressure for the calcium group and the placebo group. And I'm going to work out for myself the pooled variance to start off with. So it's n1 minus 1, 12 minus 1 times s1 squared, n2 minus 1, 15, 16 minus 1 times s2 squared over the n1 plus n2 minus 2. That comes to 33.34 as my s pooled squared. So the observed value of the test statistic then is going to be x1 bar minus x2 bar minus mu1 minus mu2 over all s times 1 over n1 and 1 over n2. Now, the one thing I haven't mentioned here is that I will have hypotheses here. So I've got the means decided here. I haven't stated my hypothesis, and I should do that. H naught is going to simply say that mu1 minus mu2 is equal to 0. And I'm assuming that my actual difference for the men with calcium, which is mu1, is bigger than the one without calcium. So I'm saying this is bigger than 0. So the order I'm subtracting in here is again x1 minus x2. And so this works out to be my observed test statistic is 1.846. So the p-value here, note the order here is bigger than in this case, so the direction here is also bigger than for my p-value. And so this comes from R to be 0.0382. It's a one-sided test, so my significance level is 0.025 by default. And so here there is insufficient evidence to reject H naught, the null hypothesis. we conclude there is no difference here. In other words, calcium does not lead to a significant reduction in blood pressure. Now, the equal variance assumption, the various tests in R, you will find some in your labs. One's called Bartlett's test, another is called Levine's test. You can use those. And so each of these tests will give you a p-value on which you can base whether the assumption of equal variance is supported or not. So H naught will essentially say that sigma 1 squared over sigma 2 squared is equal to 1. In other words, that the variances are the same. And H1 will say that these sigma 1 squared over sigma 2 squared is not equal to 1. So it's either bigger than 1 or less than 1. And so if I reject H0, that means the two variances aren't equal. And I reject or not reject based on the p-value I get from the test. But another rule of thumb essentially is if I look at the variances, look at the ratio of the variances, the larger to the smaller, then that ratio should be less than 1.5. So I can tolerate a ratio of 1.5 or so and still assume equal variance. Anything bigger than 1.5, then I'll doubt the equal variance assumption. That's a rule of thumb. So you can use either of those. So if you have the tests available, use the tests. Otherwise, this rule of thumb will work as well. Confidence intervals for population means we'll do in the next lecture. Thank you.